Hi class, it's Bill back with another video on recursion. We started in the last one talking about some of the basics, some of the issues with recursion. We looked at the how to do some tracing with recursion. We looked at stacks and how that's affected by recursive calls. So all that was a good start. And then we started looking at backtracking. We talked about the fact that brute force algorithms especially will often try every possible path. So eventually you can write in your base cases the fact that you just give up, right? This isn't working out, so I'm just going to give up at this point. And then that means a function will return, right, which takes a call off the stack. So it kind of backs itself up, right? It's as if it's sort of the little robot sort of backs itself up and tries a different path. If you wanted to try to get your way through a maze, one possibility is go right as much as you can. And if that eventually runs into a dead end, then back up to the previous intersection and then go straight. And if that runs into a dead end, then back up to the last intersection and go right. So you can have this idea of backing up and trying again, and eventually you'd get out of the maze. Now, you might take a long time getting out, but hey, you'll try all the paths, right? So there's ways to do that, and this traveling problem is a good example of how you can do that brute force with a recursive algorithm. So the problem is here, this simple problem called northeast northeast, or a northeast travel problem. The idea here is you have this starting point down here in the purple, and you're trying to get to this point pointed to by the green. So I want to take this little guy and I want to eventually end up right here. Question is, how can I get there? How many ways are there to get there? The rule is, though, you've only got three directions you can go: north, east, and northeast. So I want to go from 0, 0 to 1, 2, 1, 2, 3 to 2, 3. Right? So how many ways to do that are there? Well, we can write code that will use recursion to figure that out. And it will say, hey, first try to go north. And then if you don't have a problem, keep trying north, right? Then go north again. Then go north again and go north again. And eventually, if north stops working, try east. And if east stops working, try northeast. And by writing some simple recursive code that just implements that, amazingly will enumerate all of the travel problem options. So for instance, this code that I'm going to show you, and I've kind of fixed it up to instrument it a little more, this will eventually say, here's a path that was abandoned, right? It went north and north and north, and then when it went to this one, it can know it's never going to get here, right? It's past that point, so it abandons, and then it comes back here and goes, okay, now can I try east? Okay, sure. Now can I try north? Well, oops, nope, too far, forget that. Now can I try east again? Ooh, look at that, I got there, right? So it has abandoned paths, and then it will have some successful paths, and it's doing this in a brute force way, and backtracking will sort of ensure that you don't overdo the stack. So let's look at the code real quickly. First thing, when you're looking at a recursive call, how do you know this is a recursive method? Well, there's more calls to travel, all right? So you know there's a recursive call here, recursive problem. So let's look for the base cases. Usually they're done first. Well, we have two base cases here. One is we're there, right? We actually hit the target. So if we hit the X and the Y of the target, then we're done. So we actually print the whole path that we've been saving, right? So we save that. Now notice that this is using a global path, right, to make life easy. But we just say, hey, if we got there, hooray, let's print it. And then, of course, don't recurse, right? So of course it's a base case, it doesn't recurse. Another option though is if X has gone too far or if Y has gone too far, then we know there's no way we're getting there. We've overshot it, right? So in this case, we do nothing, we just abandon. Right? We simply say, hey, return, right? Nothing. So this is one of those backtracking moments, right? Either way here, either we found the thing or we gave up. In either case, return and then, let the next thing try to do its job and see what it can do. But if you need to keep looking, then first try traveling north. Then try traveling east. Then try traveling northeast. But remember, the way that recursion works is this is going to be called, and then it's going to try north, and then that one's going to try north, and then that one's going to try north, which is the reason that on this one, all the norths were together, right? It's going to keep pushing in the same direction because every recursive call is going to say, now try north, now try north, now try north, now try north, until one of them drops out and backtracks, and then it can try something else. The odd thing though is that's it. That's all the code, right? So if you're there, stop and say yay. If you're past it, abandon and just return. Otherwise, keep looking. Try north, try east, try northeast, and see how it goes. That will solve all of the problem by itself. Wow, right? Kind of interesting. So if you look at how it's traversing, you're going to run into a lot of dead ends, and you're going to run into some successes, and it's going to try them all, right? Eventually it will have tried every single possibility. Now, interestingly, let's look at how expensive, what's the cost of doing this thing? Well, remember, this is a brute force method. So it's not necessarily that recursion is causing this time problem. The problem is that it's a brute force algorithm. So it's visiting a lot of places, right? It's trying a lot of paths, which starts to get very expensive in terms of time, right? So I used a thing, and you'll have available this code, or you can write me if you want it. But I use grabbing the current milliseconds from the system, and then I subtract it after doing something, right? Subtract the current time from the time that I'd saved, and to find out how the elapsed time was. That's how many milliseconds. Now look at how this works, and we should plot this, and you could see the craziness of this curve. But if you're looking for to go from 0, 0 to 1, 1, it takes less than 1 millisecond. All of these are 1, and then all of a sudden it starts growing. And notice that once you get to just 13 by 13, the number of milliseconds gets really large. And after that, if you try even like 15 by 15, it takes so long that I finally just give up, right? Like I leave it running for a while, and then I finally say, okay, this is not getting there. I give up, stop it, right? So the solution is brute force. It's certainly a very exponential sort of problem, right? So it can't really scale to bigger traveling problems, but the recursion certainly finds the answers, and it will spit them all out. So interesting. But how about the stack? If it's so expensive in terms of time, if it takes so much time, does that mean the stack is going crazy? Well, actually, no. This is kind of amazing, right? Because of backtracking, the stack really never gets that big. When you instrument the code and put on something that actually shows every time you make a call, you increment a counter so you know how many functions are on the stack, you'll see that really it's really an n algorithm, right? It's a big O of n, because 13, it's 26. It's not growing that fast, right? So that's a good use in terms of stack, so we're not abusing the stack, but we're running a very expensive algorithm in terms of time because it is so brute force. So that's kind of an interesting one. Now let's take a quick break and let's just look at the code just so I can show you what I did with that. And so if we look at the travel problem, okay, just to show you, I did some other instrumentation to make it run. So you'll see that I put in some counters, and I can turn on and off displays like, do you want to see the timing, true or false? Do you want to see the actual stack count, true or false? Do you want to see the progress, true or false? So let me turn on progress but turn off timing, and all the rest of the code is here. You can see that I've instrumented it with all these counters and timers, but in essence it's the same code that we started with, right? The travel problem itself is the same. So let's close this and let's go compile it and go run it and just do a quick problem to show you. For instance, if I'm trying to get to a simple location, let me say I'm just going to 3, 4, 3 space 4. So you notice there's all of the ways that you can get from 0, 0 to 3, 4. Right? That's quite a lot of them, right? That's why the problem gets big. And again, starts by going, it is single-minded because every single recursive call starts by trying north again, and eventually it gives up on that and moves back. And notice eventually it'll say, wow, I've exhausted all the possibilities of starting with north. And eventually it's going to start with east, right? Eventually gets down to the point where, okay, now I'm going to try going east to start. But that took a long time, right? It had to finish all those other calls and backtrack all the way. So notice at this point when it was starting with east, the stack was back to nothing, right? Because it had exhausted all of the possibilities with the north, and it had recursed all the way back, so the stack was down to very little at that point. Okay, so that's kind of a cool example of recursion, but it is brute force, but it does illustrate the point of how it can solve a problem very nicely. Okay, so let's go back to our slides for just a minute. What about fractals? Can we look at some ways that you can do fractals? And one option here is, what if I wanted to draw this? Now these are kind of ugly, they're getting prettier as we go. I just want to draw a box and then an 80% of that size, you know, in terms of the length of a side. I want to draw another one right next to it and then another one right next to it and blah, 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 blah. Well, recursion can certainly do this. And the general idea here is the idea of recursive depth, right? The recursion depth. And the recursion depth says, hey, at some point we want to stop. So tell me a number. Tell me how many times you want to keep going in this recursive direction, and I will count it down and eventually stop. So you can set the recursion depth and eventually 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever, 12, 15, whatever we are down here, eventually it'll just stop. Also wrote this one. This one looks to me like a firebird from Native American art. So how could you draw that again? It's recursive because you make a smaller one, make a smaller one, make a smaller one. Each thing just makes itself and then says call again to make a smaller one next to it. Now this wouldn't be very hard to do with iterative solutions, right? These are simple. What if you wanted to draw this though? How would you keep track of where you were and how far you'd gone and make it flexible to where you could draw smaller boxes or bigger boxes or whatever you wanted to do? Well, now that gets harder, right? Keeping track of where you are in the thing becomes a little bit difficult, but recursion makes it really, really easy. It simply says, hey, like recurse until you're done. So let's look at some of that code because I think that's pretty interesting stuff. So let us discard our ink and let's look at this one. So in this case, this is a very simple one, just drawing the boxes. So in this case, I have a lot of constants to let me control what's the size of the child compared to the size of the parents, etc. What kind of fill do you want? What kind of whatever. So this is just setting things up. But again, the thing is pretty simple in terms of the algorithm because I say, look, if you get to 0, you tell me what recursion depth, right? You want to do 20 of these things, right? You want to keep generating children until you get all the way to 20. Well, that's great. So if I count down and I hit 0, then I'm done. Or I put in another thing that says, look, it's kind of silly to try to draw something less than 1 pixel, so I'm not going to bother. I'm not stupid. I'm not going to keep trying to draw 0 and then 0 and 0 and 0. So I'll stop in either case, either when I get to where you asked me to get or when I'm starting to make boxes that are smaller than 1 pixel, right? Either place, I'm stopping, we're done. Otherwise, set the color. This is using drawing panel that's from our textbook author, but you could use this on a normal JPanel drawing as well. So set the colors, draw a rectangle, etc., and then figure out what the new one needs to be and what size of the new one and where the new one needs to be, and then call draw box again and pass those parameters. So that's going to be a different x and a different y, a different size, and notice it's going to take the recursion depth and subtract 1. Why? Because eventually it has to get to 0. So the way that runs, you won't see it much because I didn't put any pauses in this one. It'll just draw. Okay, so it just drew. I'll run it again, but it's going to draw so fast because drawing, oops, yeah, you can't see it. It's coming up on the wrong monitor. So it just drew it instantly. What it looked like was instant for me. Very similar in this Firebird drawing, right? The recursion examples are pretty much the same. The only difference here is we're going off in 2 directions, right? So the recursive call says, hey, draw me, and then spawn one off to the left, right? Sort of spin up another one to my left, and then spin up another one to the right. Again, remember that because of the way recursion goes, it's going to draw this one and then call the left, which is going to then call the left, which is then going to call the left. So everything's going to go left, 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 left until that's exhausted itself. And then eventually those calls are going to return, and then it's going to go come back and eventually propagate right and then go right, 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 right. All right, so the backtracking, again, the stack is not overused, but when we draw that guy, again, it's going to draw so fast that you don't see it. It's just going to go, oh, here, I put a pause in this one. So in this case, we went right first, and then we went left, or whatever. The code might be backwards. So in this case, I put a little pause because it's more fun to see it actually drawing, so that you can see the approach that the algorithm is taking. Now, the last one is the most exciting one, the one that starts getting us to really understand the power that fractals could bring to us, is this thing with boxes. And this one's got some fancier code. Again, I have a pause in there, right? I have a pause of 10 milliseconds between the drawing of a box. And this one says, again, I'm going to stop when I get to recursion depths of 0 or a size. If I'm drawing 0 size boxes, stop. But it also has this thing about adjusting the hue, right? So you can make the color change just ever so slightly every time you draw another layer of boxes. Based on the recursion depth, I'll change the hue so the color changes a little bit. And then I have again here a pause, right? So I'm doing a thread sleep so you can actually see the thing draw. And then notice I first spin one off to the I think I'm going north first, right? If you look at the math here, right? I'm going up first and then down and then left and then right. So it'll try to go up and up and up and up and then eventually exhaust that, come back, then it'll start drawing one down and exhaust that, and then it'll go left. So as we draw this thing with the pause, you'll see all of that happening, but this is all the code to draw this whole thing, right? It's a lot of settings just to make sure you have a choice, a bunch of choices as how to make it work. But certainly you could put a UI on top of it, and that would be kind of neat. So let's run this thing, and I'll move it over real quick so you can see it actually drawing. Notice the whole top box was finished first, which we would expect because it was a north first, right? Go up first, then go down, then go left, then go right. So that is pretty cool, right? So that starts to say, hey, what if I turn up the recursion depth? What if it goes, one layer more? What would that be? What if I turn down the timing of that a little bit? Maybe 10 is too much. I don't want to go that fast, but I want to go recursive depth a little farther. Maybe I want to go to 8. Right? I'll save that. I'll compile it, and then I'll just show you that one more, just because I think this one's kind of fun to play with. I'll move it over quick. Here we go. There we go. So here we're seeing recursion depth of 8. So again, the hue changes. We started kind of purpley, then we moved to darker blue, then lighter blues. Again, up first, then down, then left, then right. When we're drawing this many of them, we may well want to make it not pause at all or pause only 1 millisecond. If you want to see it. But this is cool to kind of watch it develop and see, hey, yeah, that's the direction the algorithm is choosing, and why the recursion is choosing those directions should make sense to you if you are paying attention. So that's the end of our talk on recursion. There's nothing else that I have here. We're going to do, again, some exciting things with this. We're going to use it very heavily on trees. We're going to write algorithms that need it. So whether we use it in the very next project or not, this is a good topic to sort of hit and have your brain working on a little bit. And we will definitely use this in drawing fractals and also when working with our tree structures. So thanks for watching this video, and come back and watch another one. This is it on recursion, but we've got some exciting chapters ahead, so stay tuned for those. Come back and watch another video another day. I will let this one play itself out, turn off my microphone, let it play out, and then stop the video. So thanks.